At CanJam New York 2023, we sat down for a conversation with Rob Watts, the designer of the Chord Electronics digital to analog converters. The Chord DACs have a variety of unique design aspects which aim to overcome the challenges associated with producing a high-performance digital to analog converter. A lot of the details and theory behind these designs is discussed at length in his seminar, so get subscribed so you don't miss that.
So, thank you very much for agreeing to sit down with us.
Oh, it's great. It's great to be with Headphones.com. Thanks for inviting me.
For those who don't know, Rob Watts is the mind behind the Chord Electronics DACs. And yesterday at CanJam, you gave a seminar talking about the advantages and disadvantages of various different ways of making a DAC. And one of the things you talked about at quite some length was why you've done things differently, why you've made your own design, and what the advantages of your pulse array design were. Would you be able to summarize in a brief few sentences what the advantages of the pulse array are and what makes it different from other DACs?
My first answer to that is no. not in a few sentences.
Well, what would you say is the biggest advantage?
So probably the biggest advantage, well, there are two primary advantages. One is pulse array runs at the noise shaper, the heart of a Delta Sigma DAC, that runs at 104 megahertz, and normal Delta Sigma DACs will run at 3 megahertz or 6 megahertz. When you go from 3 megahertz to 104 megahertz, you can get a 210 dB improvement in the in-band performance. So you may well say, well, why do you want a 210 dB improvement when standard noise shapers at 140 dB are good enough? And the answer to that question is about small signal accuracy. And one of the things I've discovered from listening tests is that as you improve small signal accuracy to actually ridiculously small levels, in terms of what the errors actually are, you get an improvement in depth. Depth is something that I'm pretty crazy about and always have been crazy about. When I first started as a teenager getting involved in audio, the big thing that I could hear was that reproduced audio sounds flat by comparison to live sound.
Live music.
Yeah. So you listen to a organ in a cathedral, and it's a couple of 100 feet away. It sounds like a couple of 100 feet away.
Yeah.
But if you listen on speakers, it'll be 3 or 4 feet behind the speakers. It doesn't give that enormous impression.
There's a limit to what the range is.
Yeah. So this has been something that I've always been focusing upon in terms of trying to improve. And the factor that came out with this is small signal amplitude accuracy. But the crazy thing is the level of amplitude accuracy you need so that when depth stops reducing is a crazy number.
Yeah.
And you need to be able to reproduce, technically you need to be able to reproduce a minus 301 dB signal with accuracy within a thousandth of a dB,
right,
and with phase accuracy within a thousandth of a degree. And these are just impossibly small numbers. So to be able to accomplish that, you need a noise shaper that is capable of 350 dBs performance, and pulse array allows you to do that. The second reason that's very, very important is about timing and reconstruction of transient timing, this is obviously important when you're running at 768 kilohertz or going from 48 kilohertz to 768 kilohertz. But the importance above 768 kilohertz, it's also very important. So you can hear big differences when you go up to 3 megahertz, and you can hear big differences in the sound quality when you get the timing right above 3 megahertz. The benefit of pulse array, because it's running at 104 megahertz, is that it will actually reproduce a 52 megahertz sine wave.
Right.
It's actually not going to be a sine wave, it's going to be a square wave.
Yeah.
But it will reproduce that.
The fundamentals there.
Yeah, so the innate resolution in terms of timing is down to 9.6 nanoseconds. And that gives you another big benefit in terms of trying to reproduce audio correctly.
Even ignoring the actual noise shaper performance itself, are there any other DACs which are actually even running at close to those speeds?
No, not that I'm aware of.
No. I didn't think I've seen any.
You can have a PWM DAC which will run at a master clock of 98 megahertz.
Yeah.
But the actual switching frequency
Isn't that high?
is down to 3 megahertz.
Yeah.
And it's the switching frequency that the noise shaper is basically running at, not at that level. So a PWM signal will only be able to reproduce 1.5 megahertz because it's running at 3 megahertz.
Yeah. Oh, thank you. And for any of you who might be interested, Rob Watt's seminar on DAC topologies will be available on our channel soon, so keep an eye out for that. One other thing that's quite unique about the Chord DACs is the PCM reconstruction part of it, the actual Nyquist reconstruction. And that's something which is interesting because even ignoring the hardware, it could be implemented with other products. And I'm personally quite a big fan of that. I really like the M-scaler. And what I'm curious about is, why is it that you think other manufacturers don't try to do that?
That's a difficult question to answer.
Because it's puzzled me a little bit.
Yeah, but that's a, because I ought to be diplomatic about things, or try to be diplomatic about things. But I think there's a number of different problems. It's not only about high-end audio; it's about the audio business in totality.
Right.
In that people do not recognise the importance of transients. Even though if you go into psychoacoustic textbooks, you'll find, chapters and chapters based upon the importance of transients in terms of psychoacoustics, in terms of timbre, in terms of instrument separation, in terms of bass. This is all standard stuff that's been there since the 1950s, or perhaps even earlier. And of course, transients being important from soundstage left to right lateral imagery. So when I started getting involved in audio when I was at university, I was involved in audio much before that, but when I decided audio was going to be my career, I studied psychoacoustics because I felt that if I understood psychoacoustics, then I'd be a better designer, because that's what I wanted to do. I wanted to design gear. And the industry at large don't think that way. They think in terms of the performance of the ear. They don't think about the brain processing the ear's information, the data that's coming from the ears, and making sense of what's going on. So there's that aspect. The realization that transients is important, and that digital, of course, is a major problem with transients because you got one sample, the next sample, and you've lost the transient waveform. The information is there. It's just that you've got to convert a sample waveform back into a continuous waveform without degrading the information that's there. And the minute you put it into a standard interpolation filter, you degrade that information, and your transients become a little bit early or a little bit late, and that modulation causes all the sound quality problems. There's that, the appreciation of transients being important, but then there's also the side of having the design skills to be able to engineer a solution. So FPGA design skills, that's pretty rare, and being an analog expert and
an FPGA expert
is extremely. I don't know anybody that's got my, I'm not trying to blow my own trumpet, but that's got my analog skills and the digital skills. It's very, very difficult, impossible for a manufacturer to have those level of skills.
That makes sense.
So I think those are the two primary reasons.
Yeah.
Not being able to realize it, and the importance of it, and not having the skill set to execute that. FPGA stands for Field Programmable Gate Array, and it's a way of designing digital hardware using a chip that's very easy to do. So you can design digital hardware as a chip, or you can do it as an FPGA. Both routes use the same coding techniques. So when I'm designing for a chip, I'll do it in Verilog, and that can be ported to an FPGA or can be put into a design that will turn it into a chip. So it's the same process in terms of defining the design.
So one thing that's been happening quite a bit recently in the sort of audio community, I guess is the best way to put it, is that people are looking at measurements more. Measurements are becoming more widely available, and there's quite a sort of focus on a few particular types of measurements, particularly Synad, which, for those who don't know, incorporates a few different types of distortion and noise all into one figure. And I wanted to ask you sort of a two-part question, which is, do you have any thoughts on the, focus on Synad that's in the community? And when you look at a product, whether it's your own or someone else's, what are the first things that you would check? What are the first things you're interested to see how it's doing?
Okay, so Synad first.
Okay.
Now, Synad, in terms of performance, is an irrelevant measurement. Irrelevant in the sense that if you had a situation where you had 100 dBs worth of dynamic range, and that was at the loudspeaker or on the headphones, you would not be able to hear that hiss. So, in fact, probably 90 dBs is good enough in terms of being able to perceive the hiss. So a Synad figure of 90 dB is, or 100 dB, whatever you choose, is perfect. Because unless you're listening at 120 dB levels and destroying your hearing, you're never going to hear that level of hiss. So Synad as a simple measurement is completely unimportant. What's more important is that noise or that hiss, does it vary with signal?
Right.
That is fundamentally important, because if that noise pumps up and down with the signal itself, then the brain itself becomes very difficult for the brain to make sense of what's going on. Because the brain cannot then determine whether that hiss pumping up and down is the sound of the instrument or the sound of the distortion.
Right.
And hiss sounds bright. So when you've got some noise that's pumping up and down with, say, the sound of a saxophone, that saxophone will then sound much brighter than it should do. But if it's got this noise that's pumping up and down with the sound of the saxophone, the brain can't separate that sound out, and that sound of the saxophone becomes degraded. So noise floor modulation is fundamentally much more important than your Synad
The fixed
numbers.
noise level itself.
But no one ever measures noise floor modulation. And the other curious thing about noise floor modulation is that it's another one of these factors where it doesn't matter how small the noise floor modulation is, even if it's well below measurements, you can still hear it in terms of what it does subjectively. So the timbre gets degraded, the sense of instrument separation and the flow gets degraded as well when the noise floor modulation gets increased.
And this is something which is affected by the DAC topologies, and if you want to learn more about that, then watch Rob Watt's seminar once we publish it. What's next in terms of advances in DAC technologies, do you reckon? What's going to be the next jump in terms of making things sound better?
I've got several things that I'm working on.
Right.
The big project is the Ultima DAC, which will be a statement product from Chord. That's got some interesting new technologies inside that.
Is there any news on when we might see that?
When it's finished.
Okay.
So, COVID really damaged the timeline on that project. So I finished it in terms of PCB design a year and 3/4 ago, and I've only just received the PCBs.
Right. Okay.
So it's delayed everything. But now, getting hold of parts is not so much of a problem. So we can progress. But there's some brand new refinements that I've never done before built into this board. So we may find that it doesn't work, and so I have to try something else.
Right.
And,
Okay.
That's the nature of development.
Well, hopefully it does.
So,
I'm quite looking forward to hearing it.
It's going to be interesting, because I mean the coding, some of the improvements in coding I've already heard, and that's given substantial improvements. But that needs a massive FPGA,
Right.
In order to do what I've been working on. So that the last 3 or 4 years have been really, really interesting in terms of finding things out and improving the sound quality.
Well, hopefully we can see that soon. It's sounding quite exciting.
Hope so.
And one other question I have to ask you is, do you have any other thoughts on alternative reconstruction or enhancement technologies like MQA?
Oh, yeah, MQA destroys transient reconstruction.
Okay.
When you start adding aliasing at 1% levels, that completely destroys your transients. The curious thing is that the reason why some people prefer the sound of MQA is that when you mess up your transients, the brain cannot follow what's going on.
Right.
And if you cannot perceive the leading edge, things just sound soft. And some people like that softness that is being artificially generated. But it's nothing like real music or real unamplified sound. And the really aliasing is a major issue. And one of the things I've been working on is an A to D converter, a pulse array A to D converter, and one of the things I've discovered is that aliasing at very, very high frequencies, and I'm talking about in the megahertz range, 20, 30 megahertz, you have to go to ridiculous levels to eliminate the sound quality degradation of that aliasing.
Right.
And by ridiculous levels, I'm talking about 300 or 400 dBs worth of changes. And here you are with MQA with 40 dBs aliasing, which is just destroying everything. So no, I'm not in favour of MQA.
That's fair enough. Well, Rob, thank you very much for sitting down with us, and it's been
great.
a pleasure
It's
to
been a
talk to
pleasure.
you. I'm really looking forward to seeing what comes next from you and Chord. If you're interested in Chord products, they're available at headphones.com, and if you're wanting to watch Rob Watt's seminar, that'll be up on our channel soon. Thanks for watching.